This is video 14. In this video we want to consider our square wave function and how we can express it in a Fourier expansion series, a complex Fourier expansion series. So it has a value of 1 when we're going from 0 to a, and then the whole function looks like this. It has 1, then at a it drops down to 0, then it remains at 0 until we get to here, then once again it becomes 1, and it continues on in that pattern. So this is the entire function, and at this point t then, that's the period. This is the t-axis. So here's the amount of time t that encompasses the entire function, so that's capital T for the period. So the function goes from 0 to t, and we're not specifying any particular number for the period. So what we want to do then is expand this in a complex Fourier expansion series. So that involves these formulas. This one we had developed in video number 5 and its counterpart here. Now C of n, we have the limits on the integral going from, of course this is the period, going from minus t over 2 to plus t over 2, or if we want, we could have it going from 0 to plus t. And that's the value of our function. Well, that's either 1 or 0. When t goes from 0 to a, it's 1. From a to t, it's 0. So when we set up the limits on the integral, we can just take it from 0 to a, and our function is just simply 1. So let's write out then the expression for c sub n. We will have c sub n will equal 1 over t, the integral from 0 to a, and f of t is just 1, so we have e to the minus in omega t dt. So this is pretty straightforward to integrate. We will have 1 over t, and this part of the exponent comes down in the denominator outside of the integral, so we'll have minus in omega. Times e to the minus in omega t, and t goes from 0 to a. So let's put our limits in, and we have c n equals minus 1 over n I omega t times e to the minus in omega, and now we put a in for t. Then we have minus, put 0 in for t, e to the 0 is 1. So there's our expression for c sub n. Now we can modify this further. From this expression we can factor out an e to the minus n omega a divided by 2. Here's what it will look like. We will have Cn will equal minus 1 over n I omega t e to the minus in omega a over 2 times. So from here, this is going to be e to the minus in omega a divided by 2 minus, this is 1, so that would have to be e to the 0, so this one will have to be e to the plus I n omega a divided by 2. So there's our formula for C sub n, or our expression for C sub n. Looking at this, and if you remember from the past videos, you might be thinking perhaps you could set this up to be a sine function. Remember that what e to the I theta is equal to, and e to the minus I theta is this expression. So if we subtract these two, these will cancel out. We'll have this minus negative this, or that would be this plus this. We have 2i sine of theta. So the sine of theta equals e to the I theta minus e to the minus I theta divided by 2i. Now here we have e to the minus I theta minus e to the plus I theta. That's this multiplied by negative 1. So if this is multiplied by negative 1, these would be in the proper order then. And we'll get around to that in just a moment. Let's do something else. Remember from videos 1 and 5 that this equals 2 pi divided by t. So we can substitute that in for here. We'll have 2 pi over t times t. That will just be 2 pi. So we'll have ni 2 pi. So we have this, and then here we can also substitute in that is e, well, forget that part. We'll just have minus I n 2 pi over 2t times a. Of course, these cancel, so we have minus I n pi a over t. Let's write it in. And same thing for here and here. Minus I n pi a divided by t. And same thing for here, except it's going to be plus I n pi a divided by t. Now, notice that down here we have 2i, and we also have a minus sign here. So that sets this up to being a sine function. Before we do that, there's usually one more step that is taken, and that is to multiply this denominator here by a over t, like this, a over t. If we multiply the denominator by it, then we also have to multiply the numerator. So we're going to have minus a over t times this, times this, times this. So now we can take this along with the negative sign into here. And what will we have? We'll have C sub n will equal this, and this will go inside, so we'll have this and this, e to the minus I n pi a over t times a over t, and this along with the negative sign goes into here. So we're going to take in the negative sign. Let's get the numerator squared away. that will be times, and this will be plus EIN pi a over t minus e to the minus IN pi a over t divided by this 2I n pi a divided by t. So here's our expression for C sub n, and finally this part of it that is the sine of n pi a over 2. This is the same form as this expression right here, e to the I theta minus e to the minus I theta divided by 2 pi. This minus this to the negative exponent divided by 2i. So we have then that C sub n equals e to the minus IN pi a over capital T times a divided by capital T times the sine of n pi a over t divided by n pi a over t. And there is our expression for C sub n. Now, this here is in the general form of the sine of x divided by x. And that's encountered, this type of expression right here, the general form here, this is encountered a lot in Fourier analysis, and that is called the sinc function. That is the sinc of x. So this part of the formula we could just say is the sinc of n pi a divided by t. So here then, and this, by the way, this sinc function has special properties, and we will examine those special properties in the next video. So finally we have C sub n equals this times the sinc of n pi a over t. So let's make some room and put this all together. And see what kind of expression we get for our square wave. So remember that the general formula here for f of t equals the sum from n equal minus infinity to plus infinity of C sub n times e to the plus I n omega t. And now from our problem, or for our problem, Cn is this expression. So let's write it up here. Cn equals e to the minus I n pi a over t times a over t times the sinc of n pi a over t. So that is our expression for c sub n. One thing now is we determine c sub n, what is c sub 0? That's 1 over t, the integral 0 to a of 1 times e to the minus I n omega t dt, except n equals 0, so that's e to the 0, which is 1, so that's just the integral of dt, so this will equal a divided by capital T. That's our C0 term. So here we have finally f of t, and remember here we're just expressing omega naught as 2 pi, this is small t, and omega naught is 2 pi divided by big T. And that's the expression we used in here, so let's be consistent. This is 2 pi small t divided by capital T. Okay, now we just substituted omega 2 pi over capital T for omega here. That's what we had done in these part of the expressions when we were working our problem to solve for Cn. So finally we have f of t equals this summation c sub n, that's this, times this. So we're going to have e to the minus I n pi a over t times a over t sinc n pi a over t times this e to the I n 2 pi small t divided by capital T. So there's our expression for f of t. Now what happens, and that goes from n going from minus infinity to plus infinity. Now what happens when n is 0? And this is the sinc, not the sine. When n is 0, that's 1. When n is 0, that's 1. And as we'll show in the next video for the sinc function, when n is 0, that is 1. So we have a over t for C0, which agrees with our formula here. So we can just include the entire summation going from n equals minus infinity to plus infinity, and we can take this to the outside. So there then is finally our expression for f of t, and that is, and f of t was this square wave function right here. Okay, join us in the next video, and what we're going to do is look at this function in a little bit more detail, because this does occur many different times when you're doing Fourier analysis. So let's spend a few minutes on it. We'll do that in the next video. So come back, join us for that video, and we'll continue our discussion.